Bhavani madam, please check your mic, madam. Audio is not clear.
So now is working.
Okay,
Sir, his
sir.
voice is clear.
Okay. Now you please.
Okay, sir. So it's my privilege to introduce today's speaker, Bratin Ghosh. Bratin Ghosh is working professor in the Department of Electronics and Electrical Communication Engineering, Indian Institute of Technology, Kharagpur. He is an accomplished researcher in the field of electrical and computer engineering. He engaged in leading-edge research in Green's function-based computational techniques and design and analysis of efficient antennas, miniaturized antennas, and metamaterials. He was invited speaker, technical program committee member, and session chair in various national and international conferences. He served in the review board of prominent national international journals in microwave engineering. Editorial board member for the Journal of Microwave Engineering and Technologies. Professor Ghosh completed postdoctoral from the Royal Military College of Canada, PhD in 2002 from the University of Manitoba, Winnipeg, Canada. Master of Technology with specialization in Microwave Engineering in 1994 from Indian Institute of Technology, Kharagpur, India. Bachelor of Electronics and Telecommunication Engineering in 1990 from Jadavpur University, Calcutta, India. Professional experience of Professor Ghosh. He worked in industry both in India and abroad for about 8 years at various positions before he joins IIT Kharagpur in 2005. His awards and scholarship. He got University of Manitoba Graduate Fellowship 1997 and a Medal of Honor Defense Electronics Application Laboratory 2010, and I got Medal of Honor Indian Navy 2010. He is a senior member in Institute of Electrical and Electronics Engineering, IEEE, USC. He was a invited reviewer for the following journals: IEEE Transactions on Antenna and Propagation, IEEE Antennas and Wireless Propagation Letters, IET Microwaves, Antennas and Propagation, Progress in Electromagnetic Research. He has completed several research projects from DST, CSR, DRDL, KCST, SEB, LRDE, Ministry of Defense, and DRDO. With this brief introduction, I would like to welcome Professor Ghosh, Bratin Ghosh. Please, sir, please continue the session. Sir, welcome, sir, Bratin, sir, welcome.
Thank you. So thank you, Mrs. Bhavani, for the introduction. So the topic for presentation today is essentially the analysis and design of dielectric resonator antennas. I will switch off the video so that we don't conserve bandwidth there, a little bit of bandwidth there, and I will share the screen. Is this visible to everybody?
Yes, sir.
Okay.
Yes, sir.
So
you can go to full screen mode, sir.
Where is the option? Don't see somehow.
Sir, it is available in view, sir. In the top, file, edit, view is there, sir. So view, full screen. So below is there, sir. Full screen mode. Below, sir.
Full screen mode.
Below.
Control L.
Below, sir.
Is it? Wait.
Read mode.
Come down, sir.
Full screen. Yes, sir.
Yes, sir.
Thank you, sir.
Yes, sir.
So, essentially, this topic actually is leads to the culmination of our work on dielectric resonator antennas. Not the culmination in that sense that it is part of our ongoing research work on the analysis and design of dielectric resonator antennas. We want to focus quite a bit on the analysis, because like after all, it is one of the streams in which people are relatively uncomfortable in, and people think that it is difficult, and there are relatively lesser number of publications in this field, particularly from this part, or I mean, from our part of the continent. Now, the idea behind focusing on the analysis is to dispel this myth and to encourage you to take up antenna analysis in a more phased manner, or in a more gradual manner. The other thing is that it is difficult to cover the entire the details of the analysis, because it is quite a lengthy analysis. But I would try to highlight the key steps, so that at least you know the generic process in which such an analysis is done. I would also highlight some comparisons between the analysis of spherical structures and the analysis of other kind of structures. So now, before I begin, essentially what we deal with, let us go to the next slide. This is our essential configuration. So what do we have? We have a multi-layer dielectric resonator. I think most of you are familiar with the dielectric resonator literature, or what are the benefits of the dielectric resonator. I won't go to the details of that, because that is going to take me away from the main topic, which is the analysis part. But just a brief comment on that, that the dielectric resonator antennas are typically used in applications where there are where a low loss radiating structure is needed, because it has no conductor loss, surface wave loss is also not present, and relatively wideband structures with very stable radiation characteristics can be obtained by this kind of technology. We have extensively, worked on this field, and other research groups have also extensively done quite a good amount of work in this field. And now we know that this kind of antenna structures, though it is not that much currently in use in the industry sense, but it is very much a potential candidate for millimeter wave frequencies and beyond. Typically because of its low loss character and its very unique capacity to offer me an impedance bandwidth similar to the radiation bandwidth, which is not very often encountered in other antenna structures like the microstrip types, where the radiation bandwidth is a fraction of the impedance bandwidth. So this goes towards the motivation of the dielectric resonator antenna problem. Now, here our idea is to analyze one particular typical configuration on the dielectric resonator antenna which we had worked, and that is the microstrip line slot coupled to the dielectric resonator antenna. Now, before we understand that this is a multi-layer dielectric resonator antenna, it is typically an N layer. You see that it is N layer is mentioned, N layer DR antenna, then it is coupled by the microstrip line. So this is the side view, the left hand side, and B is the top view. So what we do is that whenever we see this kind of a problem, we think of what we say the problem of a radiating source in a medium. There are two complexities essential to this problem. Let me just bring up the slide. Share. Can you see this whiteboard?
Yes, sir. Yes, sir.
Okay. So there are two complexities to this problem. One, the complexity of the, I'm not absolutely a little bit new to Zoom because we usually teach to MS Team, but it is fine. So one is the complexity of the source, and another is the complexity of the discontinuity. What is this complexity? If you look at this problem, if you go back to this problem, which is if you go back to this problem, you see that this region, which is the slot region, I have to switch back. This region is the slot region, and this region is the discontinuity region. So this region, which is the slot region, is the source for the radiation, and these are the discontinuities in which the radiation gets reflected. We do not in microwave engineering like to treat the source problem and the discontinuity problem simultaneously, because essentially there are two different discontinuities. One is here, another there. If we have to treat two different discontinuities simultaneously, it becomes a big problem. It is never done. Okay. So what we do is that we take one by one. We first of all take the source, and next we obtain the electromagnetic fields by matching the boundary conditions across the source. Next, obtaining these fields, we allow these fields to be incident on the discontinuity, and we find the reflected and the transmitted, in that sense the radiated, the transmitted field are the radiated fields, I mean in the outer layer. So but layer by layer, we find the reflected and the transmitted fields in that layer with the radiated fields given by the transmitted fields in the outer layer. So this is the first step which we must remember, the separation of the source and the discontinuity. The next difficulty comes is that what is this source here? What kind of source is this? Now if you go back to our this one, our whiteboard. When we have resting on a ground plane, so this is the DRA ground plane. Now you see, I can know the characteristics of the DRA sitting on a continuous ground plane like this, if the ground plane is continuous. But here we have a discontinuity. So this is the slot region. So what I will do is that in order to write down the expression of the fields below and above, I will close this slot region. So what I will do is that I will, if I magnify the slot region, oops. So this was the original slot region. So I will close this slot region by a electric conductor so that I can write the fields here in the DRA region and there in the planar feed region. So this was our microstrip line and this was our DRA. It can consist of several layers. Now, if we do this, then we have violated the original boundary conditions which are present here. So the boundary conditions here, they are violated by doing this action. We cannot do that. So we construct what we call an equivalent problem. We construct an equivalent problem. What is the equivalent problem? The equivalent problem is that we will retain this slot. And after retaining this slot, we are going to place on this slot plus M magnetic current and minus M magnetic current. What it is going to do? You see, the original boundary conditions across this slot was E tangential upper equal to E tangential lower, where E tangential upper is present here. Here is E tangential up, and here is E tangential low. Similarly, here upperwards is H tangential up. Up means the upper problem and the lower problem is H tangential low. So the original boundary conditions read that E tangential up is equal to E tangential low and H tangential up equal to H tangential low. These were the original boundary conditions to the problem. Okay. These were the original boundary conditions to the problem. Oops, I don't know why it happens like this. Let me just not draw anything. Okay. So these two, one is this one, another is this one. They constitute the original boundary conditions of the problem. Do what I may, I have to obey these boundary conditions. Then the question arises, how does the placement of these two magnetic currents here and there help me to achieve the boundary conditions? We know that the magnetic current is given by minus N cross E2 minus E1 across any surface. Across any surface. It is given by minus E cross minus N cross E2 minus E1. Now E1 inside the conductor is 0. So if E2 is here, N cross E2 is the tangential component and E1 is 0 because it is inside the conductor. So therefore it becomes minus N cross E2. So in the lower surface, again, it becomes the second magnetic current M2. So if this is M up, where M up is here, upper surface, and this is M low. So M low is given by minus N, let's call this N1, where N1 is pointing up. And let's call this N2, where N2 is pointing down. So minus N1 minus N2 cross, what should I say this? Let us call this E3. So E3 minus 0, because inside the metal the field is 0. So it becomes minus N2 cross E3. Now you see that because N1 and N2 are oppositely directed, N1 and N2 are oppositely directed, you can see from the figure. And E2 and E3 must be the same because E2 and E3 are the N cross E1 and N cross E2, they are the tangential components. So therefore, if N1 and N2 are oppositely directed, it should be equal to, I don't know whether there is a this facility available. We can do it in MS Teams, but whether there is a zoom in or zoom out available, probably there is. But anyway, so it is minus minus of, so this is plus minus of, I can say minus of N1. So it will become plus N1 cross E3. Or plus N1 cross, sorry, plus N1 cross E3. Now, the tangential components N cross E2 must be equal to the tangential components N cross E3 because of obeying of this relationship. Therefore, the M up must be equal to the negative of M low. You can see from these two equations, this one and this one. So by placing antiphase magnetic currents across the slot and shutting off the slot by a conductor enables me to obey the electric field boundary condition. But we are left with another boundary condition, which is this. We have done nothing to this boundary condition till now. How do we solve this problem then? Then what we will do is that, you see, another thing, that in order to find out the currents radiated in the upper side, we need to know the value of the magnetic current. Because unless this source is known, this magnetic current M up is known or M low is known, this is constituting the excitation source to the problem. So unless this is known, we cannot find the radiated fields. So we have to find the magnetic current. But we do not know the magnetic current, and thereby we do not know the radiated fields. In order to find the magnetic current, we assume now that the magnetic current is a point source. It is a point source. It is a delta function source. So the next thing is to think, or to this one. The next step is to think that the magnetic current, it is replaced by a delta function source. Oops. Okay, as long as you can read it. So it is replaced by a delta function source. Now we find out the radiated fields due to this delta function source. What are the radiated fields? What are the radiated fields due to this delta function source? Let me okay. So we now find out what is the radiated fields due to this delta function source. This is called the Green's function to the problem. Green's function. It is nothing but the response of this network, so to say. The antenna is a network. The response of this network to the unit impulse source. Once this response is obtained, we can find out the true response, the true, like the true fields by convolving the Green's function with the magnetic current and integrating it over the area of the slot. So this will give me the true magnetic field H10 up. The true magnetic field is obtained by convolving this Green's function. This is the Green's function. By convolving the Green's function with the magnetic current, which is unknown. This is the actual magnetic current. Actual slot magnetic current. It is unknown to me. And because this is unknown to me and it is integrated over ds prime, which is the area of the slot. Now, because this is unknown to me, this is also unknown to me. Whereas this is known. I mean, this is found out. It is not known, it has to be found out by me. The unit impulse has to be found out by me. But then after I find out the H tan up, I, in a similar manner, will find out H tan low. So I will write H tan low to be, let us run this. We have a minus my, because in the lower surface we have a minus component to the magnetic current times ds prime. Now note that this Green's function and this Green's function are different. This is for the upper part of the Green's function. We call it, instead we call it G up. Let us call it G up. And let us call this G low. Now the other question is how our Green's function itself is represented, this big G. As I told you, the Green's function tells me what is the fields radiated due to our delta function source. In its denominator sits the particular source component. So here we have the source. Here we have in the subscript the field. Now the source, you see, can have, let's remove this. The source can be Jx, Jy, Jz, or Mx, My, Mz. So these are the 6 orientations of the sources which sit here. What about the fields? The fields can be so these are the fields. These are the fields which sit there. In this case, we are dealing with the spherical coordinate system. We will have the r theta phi components of the currents and the fields. But in total, we can have 6 cross 6, 36 Green's functions. So 36 Green's functions are possible. Oops. 36 Green's functions are possible. That's right. So the next question comes: how we determine this H tan up? Because this magnetic current is not known, H tan up is also not known. In order to determine H tan up, we have to equate these two across the slot, this one and this one. So this is the equation stating H tan up is equal to H tan So we have to equate H tan up and H tan low. Please don't confuse with E3. So this is my H tan low. This is called in electromagnetics the H field continuity equation. So this is called the H field continuity. I don't know why this problem happens. H field continuity equation. Okay. By solving these two H field, by writing this H field continuity equation, this magnetic current My, which is unknown here, minus My, and this magnetic current My is solved using the method of moments. So this is the generic idea how to solve the slot problem, and this is universal across the literature, whether it is a microstrip slot, whether it is a slot under the DRA, or whether it is a waveguide slot, all are attacked according to this general methodology. There is no difference. The difference or the uniqueness of the problem will come in these functions. The difference of the uniqueness of the problem will come in these two functions, here and here. If it is a microstrip slot, it will be becoming one kind of Green's function. If it is a slot underneath the DRA, it will become the other kind of Green's function. So these Green's functions are problem specific. It is like the impulse response to any kind of network in low frequency. Once I know the impulse response, I can find the input by convolving the impulse response with the input. I can find the output by convolving the impulse response with the input. So the impulse response contains all the information of the problem. So therefore, once the Green's function is known, everything else is known. Everything else is found out. So therefore, our focus is to find out the Green's function. Okay. So my focus is to find out the Green's function G low and G up. If I can find out these Green's functions, we have solved the problem. So at least this, up to this should be understandable. Now let us go back to the problem. We do not now in this situation concentrate on the lower part of the Green's function, because that is the Green's function in the substrate part, which is this part in this region, because that has been done years back, 30 years back. Okay, so that is not our concern. The planar people have worked on the microstrip slot on the microstrip ground plane for a long time. So this is well established in the literature. So we are not going to dwell on the lower Green's function. Our main concern is to find out the upper Green's function, or the concept of a magnetic source, magnetic current source, radiating, sitting on or residing on a ground plane on which the DRA resides. What is the nature of the radiated or the scattered fields? That is our main concern. Okay. In order to now follow this route, we note that there are essentially two different ways in which how this route is followed. And then those two different ways are essentially, again, we have to go back to the whiteboard. Let us clear it. Now you see that when we want to find, our main concern now is to find out the, due to this magnetic current, we have, let's change the color. Oops. I don't know what is this, the bug or something. Let us, we cannot draw this. So, what we do is that we have, what did we land up to? We had a current source, M. This is my slot. This is my slot, which is oriented along the y direction. It is oriented along the y direction, and thereby we had a y component of the magnetic current. Okay. So now we want to find this, due to this My, the radiated fields in the presence of the DRA. When we try to do that, we encounter two different routes which are followed in the literature. One is the route of the scalar Green's function. And another is the route of the dyadic Green's function. What is this scalar and dyadic? We know that the Helmholtz equation is given in the rectangular coordinates as this, or particularly we can write grad square plus k square A equal to minus G. Now you see, therefore, what does this Helmholtz equation tell me? What does this Helmholtz equation tell me? It tells me that given a source J, we will first find out the vector potential A, and from this vector potential, we will find the fields E and H. We all know this. Now, in order to do this exercise, we need to find out A first, and secondly, we need to find how this A is linked with the radiated electric and magnetic fields. What do I mean by these statements? How this A is linked to the radiated electric and magnetic fields? For instance, we know that if A is z-directed, A has a z-directed component, then we have our Tm to Z mode. In which Hz equal to 0. You can verify this from the rectangular waveguide field equations. Similarly, if I have a magnetic current source, then my wave equation will change, and we can write grad square plus k square F is equal to minus M. Please check this. There may not be a minus sign here. That I am not sure. Using duality, what will happen? but please check this minus sign. Okay. So, but what is important to us now is that if Z is if F has a Z component only, then we will generate a TE2Z mode. That is what is more relevant to us. Under which condition is Z equal to 0? Under which condition is Z is 0? How does this help me in order to solve the Green's function problem? This helps me in order to solve the Green's function problem, because if A is Z directed, I will not calculate the amplitudes of the TE2Z modes. Similarly, if F is Z directed, I will not calculate the amplitudes of the TM2Z modes. Sorry, the amplitudes of the TE2Z modes. So again repeat. If A is Z directed, because it is generating the TM2Z mode, I will not calculate the amplitudes of the TE2Z mode. And if F is Z directed, I will not calculate the amplitudes of the TM2Z mode. In case I made a wrong statement, I will not calculate the amplitude of the TM2Z mode. But in order to make this distinction, we have to look at the orientation of the source. Here, this is the source. This will save me a lot of computation time, because I will not waste my time in calculating unnecessary modes. Note that if I do not note this feature and brute force calculate all the modes, I will still arrive at the correct solution, but it will be a lengthier route. The groups which take advantage of this feature are the scalar Green's function group. We essentially in our group work on the scalar Green's function. Other groups can say, I do not care this correspondence. This correspondence is not meaningful to me. I won't use or exploit this feature. Groups which do not exploit this feature are the dyadic Green's function group. On the face of it, now you will say, what is the use? Why won't I make this feature? Because using this feature enables us to calculate only necessary modes and spend computation and reduce computation time. But while you reduce computation time, you must also note that your code does not become general. What do I mean by your code does not become general? Instead of a rectangular slot now, if I have a slot like this, annular slot, or a shorted annular slot, because it is shorted at this point, it is shorted at this point. Imagine this to be a circle. Okay, I don't want to just do that again. So this is a circle. So if your source changes, your formulation changes again, because now you will again look which are the components which are responsible for reduction in the number of modes. So the scalar Green's function groups actually spend like a considerable effort in reducing the number of modes in their computation. The dyadic Green's function says, I will not do anything to that, because I will make my code general. I will take any alpha oriented source, any source which is alpha oriented. It can be art directed, theta directed, phi directed, and I will write down my electromagnetic field radiated by the alpha directed source. I will calculate unnecessary modes, and my computation time will be larger than the scalar Green's function group. But I will win on the generality front. Once the code for the dyadic Green's function is written, it can be used anywhere. This slot any arbitrary orientation of the slot. But because one of the main advantages of the Green's function, why we work the Green's function technique, why we forsake the HFSS route, one of the main concerns is its speed. While HFSS will give you a solution after 10 minutes, Green's function will give the same solution in 10 seconds. So the critical concern is the speed. So thereby, the scalar Green's function is by far more popular than the direct Green's function. But it is not to say something is good, something is bad. Everything depends on the application. Okay, it is not that scalar Green is good, dyadic bad, or dyadic bad scalar, or dyadic good scalar bad. It is nothing like that. Okay, it will depend on the application, but because of its like relative speed, the relative speed of the code in the scalar Green's function, this has been much more widely investigated than the dyadic Green's function. Now, the actual part of the problem. Basically, we have to spend a little bit time in the introduction, otherwise you won't follow what is going on. So now what we do is let us go back to the slide. So what we do is that we resolve, or make use first of all of the image theory. So we reflect the DRA on the lower surface and replace the magnetic current by its image. So it is minus 2my. Why we do this is not apparent now, but it will be apparent clear. You can argue that I would actually use this whole ground plane and apply the boundary condition over this ground plane as well. And I will analyze half of the DRA. I will not analyze the full DRA. One can argue, but you will see why that is not done. In fact, this will also expose one of the very important aspects of the Green's function, which is the use of the image theory and the use of the fact that the ground plane is relatively large or theoretically infinite. Now, what we do is that we break up the solution, as we said, into two parts. One is the particular solution. The particular solution alone will represent the source radiating in an unbounded dielectric medium. And it is similar to the single layer DRA. What does that mean? It means that in the dielectric layer, mark this carefully, in the dielectric layer the slot is located, which is epsilon r1 mu r1. You will assume that this slot is radiating homogeneously. There are no layers like this. It is radiating homogeneously in a homogeneous medium of permittivity epsilon r1 and permeability mu r1. The next step is to write down the homogeneous solution. After this particular solution is found, as I told, the source is removed. I told you we cannot take the source and the discontinuity at the same time or simultaneously. So after finding out GP, the particular solution, the source is removed and the homogeneous solution is found, which accounts for the dielectric discontinuities. Let us now see how this is done. Okay. You see now that the slot is in the, first of all, in the rectangular coordinate system. You see the slot here? It is in the rectangular coordinate system, while my DRA is in the spherical coordinate system. I cannot work on two systems simultaneously. Because my main antenna is in the spherical coordinate system, I will convert the rectangular slot in the spherical coordinate system, and this is what I do here. So I have the rectangular to spherical transformation at theta equal to pi by 2. Theta is the location of the source, theta prime is the location of the field. Anywhere where it comes, the primed coordinate refer to the location of the field and the unprimed with location of the source. So now we see that we have noted for the rectangular coordinate system. Again, let us go back. In the rectangular coordinate system, we have seen that how the AZ and the modes, or the FZ and the modes, AZ and the modes, presence of FZ generates the T to Z modes. In the spherical system, if I have a spherical system here, if this is my R direction, the modes in this surface, let's say this is an epsilon R and this is epsilon naught. The modes in this sphere are given by TE to R and TM to R modes. They are the spherical DRA modes. TE to R means there is no ER. ER is 0. Transverse electric to R, and TM to R means HR equal to 0. So now you see, just like FZ will generate the T to Z modes, FR is going to generate the T to R modes. If a magnetic current is located, is oriented along the R direction, it will generate only the T to R modes and not excite the TM to R modes. That is what I wanted you to appreciate at this level. So the FR will produce only the T to R modes. We don't have an electric current source, so we don't have a one-to-one correspondence between that, between the JR and the TM to R. But had there been a JR, that JR will only generate TM to R modes. But all our sources in this problem are magnetic. However, the TM to R modes are going to come into the picture. You are going to see how. Let us go back to our slide. You see, we have, when we break up the magnetic current, which is directed along the Y direction, it will have a undirected component and a phi directed component. A slot along the Y direction. This is my radial coordinate system. Let me draw it twice. Let me see whether that works. But at least this works. Imagine this to be a sphere, okay? So all these things are not there. What is, oops, then the whole thing vanishes. This is a sphere. I have a slot like this. This is my Y direction. This is my slot magnetic current in Y. So this I will break up into two components, one along this direction and another along this direction. So let's call it so this magnetic current, which is directed along the Y direction, is broken up into two. Now this MR is going to generate, because it is a magnetic current, it is going to generate electric vector potential FR. Just like in the rectangular coordinate system, MZ will generate FZ, and a JZ is going to generate AZ. A JZ generates AZ and an MZ generates FZ. So here MR is going to generate FR. This is generated by MR. And therefore, this magnetic current is going to generate only the T2R modes. It is going to generate only the T2R modes. That is our main, one of the purposes of this scalar Green's function. Now you see, we go back to the presentation. MR excites the T2R mode, and M5 will excite both the T2R and the TM2R mode. So there are three Green's functions which are required. One is the GMR-FR, because it is generating only the T2R mode, so we need only FR. For the M5, we need both the T2R and the TM2R mode. GM5-FR denotes the T2R mode, and GM5-AR denotes the TM2R mode. Now it is clear how the scalar Green's function is working. So we take component by component. Okay, but the key step is here. M1 excites only the T2R mode and not the TM2R mode. So now the generic nature of the Green's function are written down. What do we mean by generic nature of the Green's function? It is that for we have only the source, we don't have any discontinuity. We have only the source M5. You see M5 FRT. So this M5 for R greater than R prime and R less than R prime. So again, let us go back here. If I have an M5, see this M5, you forget about MR. So now let me erase this. We only have an M5. We are concentrating only on this component. So this is my location of this M5. So this is R prime. This distance is R prime. So before R prime, we encountered the point R prime is equal to 0. And after R prime, we encountered the point R prime equal to infinity. This layer, remember, this is not a DRA layer. It is just a spherical configuration. Okay, no DRA, because we are dealing with the particular solution is present. So what do? We write down the fields. Now, when you write down the generic expression of the fields in the Green's function, you must always remember this rule. This is again universal, and that is, if the point of interest includes R is equal to 0, this region R less than R prime includes the point R equal to 0, because it includes the point R prime equal to 0. Only the Bessel function, here it is called the Shelkunov type Bessel function. This will be finite. This point, this region, on the other hand, includes the point R is equal to infinity. There we will only have the outgoing Henkel function, because this outgoing Henkel function will satisfy the wave propagation characteristics at R prime is equal to infinity, which is the radiation condition at R prime equal to infinity. It is only the second kind of outgoing Henkel function will satisfy the radiation condition. And where does this come from? This Jn cap, Hn cap, this comes from the solution to the spherical vector wave equation. Just like, which is the spherical analog of Helmholtz equation, which we wrote down, grad square plus k square psi is equal to minus j, or grad square plus k square a equal to minus j. The spherical analog to that equation with j equal to 0, with no source, so source-free wave equation, these terms come from there. This describes the azimuthal variation of the fields along the theta direction. This is called the associated Legendre polynomial. And this describes the azimuthal variation of the fields. The double summation works to take into account all the modes in this formulation. The double summation works from n equal to 0 to infinity and m equal to minus n to plus n. This summation from m equal to minus n to plus n occurs because Pnm cos theta is 0 outside that range. Pnm cos theta will not exist outside the range m equal to minus n to plus n, and thereby those limits. This is the grammar of the spherical coordinate system. This grammar is used everywhere in the spherical coordinate system. So if you ever work on the spherical coordinate system, you cannot overpass this grammar. Okay, so we write down the three generic functions for the fields. Don't bother about this function because this is found by matching. You see, this is constant. R prime is a constant. It denotes the location of the magnetic current, or the location, the radial location of the slot. R prime denotes the radial location of the slot. So this is a constant. It is found actually by matching the fields across the slot region, making the E tangential 1 equal to E tangential 2, which is E phi 1 equal to E phi 2, and H phi 1 equal to H phi 2. That's how these constants are evaluated. So don't bother about these constants. In fact, if you don't take these constants at all, that is absolutely fine. They will automatically come when you match the fields across the source. But note this ANM1, this is the unknown amplitude of the Green's function which we have to find. Similarly, we have M phi ARP and MR FRP. They are all the same kind with only different unknowns ANM2 and ANM3. So now, this is the equivalent problem for the particular solution which we already drew. Fine, let us not worry about that. If you look at Harrington, the next step is to find out how the vector potentials A and F, they are linked with the electric and magnetic fields. So this is the relationship which is given in R.F. Harrington, which connects the magnetic vector potential and the electric vector potential with the radiated fields. ER is theta E phi and HR is theta H phi. Then the evaluation of the unknown constants in the particular solution. When we evaluate the unknowns of the particular solution, which is the ANM1, ANM2, ANM3, we match the fields across the interface. Because the source is located at R equal to R prime, we match the fields E phi 1 equal to E phi 2. Now, and E theta 1 minus E theta 2 equal to M phi. Now, we must note that E phi 1 will come in double summation. There is a whole bunch of infinite modes in the left hand side, a whole bunch of infinite modes on the right hand side. So this is not a very simple equation. It looks simple, but we have to isolate each and every mode from there, because you note that these double summations are going to come from these equations, and because A and F come with double summations, these double summations are going to be retained in ER, E theta, E phi, and the magnetic field components. So in essence, this will be a double summation on this side, double summation on that side. In order to now pick up or solve for one particular mode, because we don't want all the modes in the summation, the most important step in the Green's function is to get rid of the summation. We have the double summation, we have to get rid of the summation. Because if you cannot get rid of the summation, you cannot find the amplitude of the nth mode. Okay, I want to find out what is the amplitude if m equal to 5, n equal to 2. That is my central problem. I cannot find that if the double summation is present. So my first step is to get rid of the double summation. In this context, we will use what are known as orthogonality properties. The orthogonality properties are similar to what we encounter in the rectangular coordinate system, which is the orthogonal between the sinusoidal and the cosinusoidal functions, or between two sinusoidal functions with different eigennumbers, like sine k1x, sine k2x, integrating from 0 to 2 pi dx, sine k1x, cos k1x, integrating from 0 to 2 pi dx. Those kinds of functions are used in order to multiply the equations and integrate. Now, it is easier to get rid of the summation over the eigenvalue for the exponential, which is m, because exponential functions are basically sinusoidal functions which are expressed in exponential form. So we know that exponential times another exponential, e to the power jm phi times e to the power jm dash phi is 2 pi if m equal to m prime and 0 if m not equal to m prime. With this token, we can drive out one summation, but we have another summation, and those two summations are coupled. That is, we have the associated Legendre polynomials. That is where the difficulty comes from. When we go to the orthogonal properties of Legendre polynomials, they don't look simple as the relationship between the exponentials here. They look rather formidable. And actually, they are a bit tricky to handle. If I would not say difficult, I would rather use the word challenging. Okay. So you see, these are the orthogonal properties. Orthogonal properties are like the pillars to your building. You have to use them in order to make the building stand on the ground. So you now see that in order to use this kind of property, we have to change these equations. The key step is to change these equations, which are here. It is difficult to show it here, but the derivation is very, very long. So in order to change these equations to actually enable me to use these orthogonal properties, I have to tailor those equations in such a manner, okay, such that these orthogonal properties can be used and get rid of the summation over both m and n. You again see now why I talked that the removal of the ground plane is significant. We said that we have to remove the ground plane and use image theory. You now see the reason behind that, the rationale behind that move. You see that the limits of this integral run from 0 to pi. If the ground plane is present, your limit will run from 0 to pi by 2. But 0 to pi by 2, we do not have any orthogonality relationships of Legendre polynomials. Therefore, you have to always run the integral from 0 to pi and remove the ground plane at the very onset of the problem. So there are two orthogonality relationships of the Legendre polynomials. This is 1 and this is 2. We won't go to the steps of how this is removed because that is impossible to show in a kind of presentation like this, because it's a very, very lengthy procedure. But if you try, you should be able to do that. But you have to try quite a bit. Okay. The other thing which we encounter while we are in this process of driving out the summations is Wronskians. These Wronskians come in all shapes and types. They are essentially linking the Bessel-Henkel with their corresponding derivatives. You see, one is the underivative part and another is the one with the derivative. The first one is without the derivative and the second one is with the derivative. This is not the only Wronskian. There are many, many Wronskians. Whenever we meet such Wronskians in the formulation, we make use of the property of the Wronskians and we substitute the right-hand side j by 2, 2j, like that. So some kind of relationship exists between the Bessel-Henkel and their corresponding derivatives, and they are the Wronskians which are used whenever we meet the appropriate Wronskian. So that is its significance in Green's function. So then on simplification, ultimately the unknowns ANM1 and ANM2 appears like this. And then for a delta magnetic source M5, which is the Green's function, when we substitute this delta magnetic source here, ANM1 and ANM2 takes this form. Okay, these are the unknowns of the particular Green's function. So then the particular Green's function can be written GM5 FRP and GM5 ARP. So these are the unknowns. They are written after substitution of the unknowns with small ANM1 amplitude and small ANM2 amplitude Now we have another Green's function, which is GMR FRP, and its unknown was capital ANM3, if you recall. Because MR FRP directly satisfies the wave equation, I told you grad square plus k square A equal to minus J. So you see in the spherical wave equation, it is grad square plus k square G by R or A by R equal to minus M by R. So this is the spherical wave equation from which directly GMR FRP is obtained after matching the unknowns across the source. Okay. So because the GMR directly satisfies the wave equation, we can find its solution, okay, by matching the fields across the source region, which is GMR R. So now what we do is we write down the potential functions for the homogeneous case, which is exactly in the same manner, but with an exception. Now there is no source. We have the different layers. This is the first layer, R less than R1. You remember our DRA configuration. R1, R2, R3. Now there is no source present. This source is absent. We have only a whole DRA, which is this one. R1, R2, R3, and we are concerned about finding the scattering from these interfaces because we are dealing with a homogeneous solution. Now let us go there. So these unknowns are these Green's functions are again written down generically because this first layer contains the point R equal to 0. It is the Shelkunov type Bessel. And the last layer contains the point R is equal to infinity. It is the outgoing Henkel. In intermediate layers, reflections are going to take place. So this is expressed by two constants, VNM1, VNM2, in between R1 and R2. And this is the Shelkunov Bessel of the first kind, the Shelkunov Bessel of the second kind. If you are interested in doing this kind of research, your first step is to read Harrington, the chapter on spherical wave function. You do not have to read the whole chapter. You can start from the spherical vector wave equation and turn back to the end of Harrington. There are relationships between the spherical wave functions. But I will not give you any false hope. This is not a cakewalk. But at the same time, it is not something which is undoable. You need to have patience. You need to have motivation. Okay, so to sit with the mathematical equations and work slowly one at a time. Everyone in the world precisely can do an HFSS simulation. Okay, our country was typically very, very rich in computational electromagnetics and in Green's functions. Unfortunately, now the students find it very, very challenging, and I don't blame this country in many other parts of the world as well. But please do not forget that we had as a country a very rich heritage in computational electromagnetics. Okay, I don't want to mention the names, but a few names can be Professor K.C. Gupta, the late Professor K.C. Gupta, Professor Garg, Professor B.N. Das, they all worked extensively on antenna analysis. Okay, so please, I would urge you, at least some of you, to take interest in this field. Okay, so the textbook to start with is with Harrington, and then move over to advanced texts slowly, but it will take time. So you see now the other part of the Green's function, which is the GM phi ARH. Okay, they are given by the other set of unknowns, CNM1 to CNM2N. So these are the Green's function relating to M phi, and this is for the T2R mode, this is for the TM2R mode. Then we have the Green's function related to MR, which is only the T2R mode. Therefore, it is R homogeneous. H stands for homogeneous and R is the FR. So these are the unknowns of the homogeneous Green's function. So then we match how many unknowns there are there in each Green's functions. We have a total of 2n n minus 1. So 2 into each unknown from here to here has 2 into n minus 1. So 2n minus 2 plus 2. This unknown and this unknown. So we have a total of 2n unknowns here. 2 capital N. 2 capital N, this n, where n is the number of layers. So the three Green's functions will have a total of 6n unknowns. And we have to determine all these 6n unknowns. And again, we'll have the double summation. Again, therefore, the boundary conditions and the orthogonal properties are used to evaluate the unknown constants by eliminating gradually the double summation. We have to make the double summation vanish from the homogeneous solution as well. So these are the boundary conditions which we use in order to find out the unknown constants in the homogeneous solution. E theta I comes from the particular solution. We have evaluated the particular solution. This is the incident field from the particular solution. Remember that the slot is not present. The slot is not present, but the incident field illuminates the different layers of the DRA. The incident field falls on or is incident on the n layers of the DRA. This is the scattered field in the first layer, which is the reflected field in the first layer. This is the transmitted field in the second layer. So we find out that the total field on the left hand side is incident field plus the reflected field, and the total field on the transmitted side is on the layer 2 is the transmitted field. It is the transmitted field. So we match all the tangential field components, which are E theta, E phi, H theta, H phi, because these are the tangential field components across the layer interfaces. Next, at R equal to R2, we don't have an incident component. We have only a scattered field component and a transmitted field component. Okay, if we go back again to the diagram. In this layer, in the first layer, we have the incident field component from here, scattered field component, transmitted component. In this layer, in this particular where the hand symbol is, in this layer, we don't have an incident field component. We have a transmitted component going that side and a reflected component going this side. We equate this component and that component. That is what we do. So that's why it is written E theta 2s equal to E theta 3s. And likewise at the nth or the last interface. Note again the generic form of the Green's function where it includes the point r equal to 0. I have only the Shelkunoff of Bessel. Where it includes the point r equal to infinity, I have the outgoing Henkel. Everywhere, here, here, here. The same generic nature repeats. Okay. Now, again, the orthogonal properties, which we are not going to dwell on, but helps us to find out the solution to these equations. So we find out that after applying the interface conditions, the above orthogonal properties are used, and this generates two equations for the two potential Green's functions, each set having 2n equations. So you see, we have the set of equations corresponding to G m phi FRH. And another set of equations will be corresponding to G m phi ARH. You can ask the question, why are they not coupled? Why does that T to R, you see, it is saying that G m phi FRH will give the T to R mode reflection amplitudes. G m phi FRH gives the T to R mode reflected amplitude. G m phi ARH gives the TM to R mode reflected amplitudes. One can say that why they are not coupled. An investigation of the spherical geometry shows that the T and the TM modes are decoupled, which means that if the incident field is of the T type, the reflected and the transmitted fields will also be of the T type. Similarly, if the incident field is of the TM type, the reflected and the transmitted fields will always be of the TM type. This is referred by the technical word that T and the TM modes are decoupled at the spherical interface. This luxury is not there in many coordinate systems. For example, in the cylindrical coordinate system, this kind of feature is not there and makes life, I will say, not say difficult, but it makes life go in we have to take a different route to the problem. The reflection coefficients here in the spherical coordinate transfer to reflection matrices in the cylindrical coordinate, because an incident field on a dielectric cylinder will generate both T and TM modes. If the incident field is a T, the reflected field will be a mixture of T and TM modes. Anyway, we are not going to go to that details of that. I will just, because we are passing by the mode decoupling feature, I just wanted to compare the two coordinate systems and show that this kind of behavior is typical and characterizes the spherical coordinate system. Okay, so now these are the set of equations we get corresponding to matching of G m phi FRH. You note in this equation that all the terms on the right hand side are 0, except for equation number 1 and equation number 4. These A and M1 come from the particular solution. They arise from the particular solution. And we have therefore a matrix. Okay, we can represent this by a matrix where all these will be in a column vector, BNM1, BNM2, BNM3 in a column vector, and these will be JN, K1, all these things will be in a like n cross n matrix or a n cross 2n cross 2n matrix. Okay, and these unknowns again will be in the column vector on the right hand side. So now let's come to that later. So the representation is in this form: delta TENM, delta TEN times this transpose, that means this is in the column vector form, will be equal to this transpose, that is the excitation term. Out of the right hand column vector, all the terms are 0 except equation number 1 and equation number whatever that is, equation number 4. we see now how the concept of modes arise from here. The concept of modes arises when there is a solution to the field without an excitation. What does this actually mean? What does this actually mean? It means if you consider a RLC circuit or an LC circuit, okay, there will be a solution to the L and C at the resonant frequency irrespective of the excitation. So at resonance, a finite solution of the fields exists without excitation because energy is transferred from the inductor to the capacitor and capacitor to the inductor, because there is no loss here. I have not considered dielectric loss. I have not considered conductor loss. None of the things are lossy here. So therefore, this energy transfer is going to happen infinitely in the absence of excitation. So we set the excitation terms to be 0 and calculate the determinant of this. So you see the determinant of the delta Tn, which is this matrix, which is this matrix here, which is here, set to 0. The roots of this is going to give me the modes of the DRA. Similarly, setting the delta Tm, the other Green's functions. We told you there was the other Green's function, which is for the Tm modes. Gm phi AR. Setting the determinant of that Tm mode matrix to be 0, we get the characteristic equation for the Tm to R mode. The Tm matrix is shown here. So now the modes of the spheres are evaluated. Now you see that when you evaluate such roots of this equation and of this equation, these roots come in complex numbers. They are not real roots. Any antenna which radiates, an antenna radiates, any structure which radiates in reality has complex resonance frequency. It will never have a real resonant frequency. The reason for this can be appreciated from such kind of reasoning. If I have a rectangular resonator, and this is of dimension A, and this is the X, and the Z axis. The characteristic equation for this reads m pi by a whole square plus n pi by b whole square plus p pi where omega r is the resonant frequency. So you see, omega r, the value of omega r is purely real. It is purely real. Because why it is purely real? Because it is surrounded by conducting, it is a conducting body, surrounded on all 6 sides by conducting walls. It does not radiate at all. Its Q factor is infinite. So its resonant frequency is purely real. But if an antenna radiates, such things is not going to hold good. Okay. For an antenna which radiates, you now see that the resonant frequencies which are calculated from here, they are not real numbers. They are complex numbers. Now, what does this complex number indicate? This complex number indicates that this structure is radiating energy. In fact, the Q of the antenna, which we want to minimize, because we want to maximize the radiated energy, is given by omega prime by 2 omega double prime. And we want to actually minimize the Q and maximize omega double prime. So now you see that the other thing, which is the mode designation. Why are we doing this? Now you will see the practical utility why we are walking this route other than the enormous speed of the Green's function. You see here that these values of the matrix delta Tm and delta Te, you see these values Mn1. All these element values, they are dependent only on this modal subscript n. See all this n? It has no dependence on m, which is e to the power jn5. So these values will only depend on n. What does it mean? It means that the azimuthal variation of the fields do not have anything to do with the resonant frequency. They have nothing to do with the resonant frequency. In fact, given the value of n from this equation, if I choose a particular value of n, it will be giving me an infinite series of roots. I label them root p equal to 1, root p equal to 2, root p equal to 3, like that, for a given value or a fixed value of n. Then I change the value of n to 2. Again, it will give an infinite series of roots. I will label them p equal to 1, p equal to 2, p equal to 3, like that. So therefore, it seems that for this hemispherical resonator, only 2 indices are sufficient. Only 2 indices are sufficient, which is n and p. But it is not. Though the characteristic equation as it is written below is independent of m, m plays a vital role. M plays a vital role in this process. What is the role that m plays in this process? M plays a vital role in this process because though the resonant frequencies are not dependent on m, the radiated fields are dependent on m. For the simple reason that the Green's functions depend on m. These Green's functions, you see their nm dependence. They depend on both n and m. And because these Green's function determine the radiated fields will depend on both n and m. However, the radiated fields are independent of p. There is no p dependence in the radiated fields, which are the ordered sequence of roots of the resonant frequency. What does this lead us to believe? It leads us to believe that if we properly select the values of m, n, and p for the T, N, M, P modes, we might be able to control the radiation characteristics if we pay proper attention to N, P, N, M, and P. Specifically what? Specifically, we may want a dual band antenna with absolutely uniform radiation characteristics at 2 bands. You see that the radiation characteristics, since they are independent of P, I will choose the bands so that they will have the same value of P. Because the radiated fields are going to be independent of P. They are independent of P. So I will choose the 2 radiation modes to have the same value of P. Okay. Or if I want to change the value, if I want to change the value of change the nature of a radiated field, I might choose the values of N, N, and P accordingly. But it is important to know that the radiation fields will depend on only N and M, and will be independent of P. So I can change the resonant frequencies by changing P, because with changing P, the resonant frequency changes. And by changing N and M, I can control the radiation characteristics. Okay, so sorry, if I use the same value, of M, not P, if I use the same value of M, I can get the same radiation characteristics by changing P only. Okay, so this keeps us to the tune. This will happen with all the Green's function. You see, N and M dependence, P independence. So this N and M dependence can be used to have uniformity in radiation characteristics with dual band or multi-band character. I will change only the value of, I will change only the value of, or keep the value of N and M fixed. I will keep the value of N and M fixed so that the radiation characteristics are fixed, and change the value of P. Thereby, all my fields are going to be the same. All my fields are going to be the same as the mode hops between different modes, as the fields hop between the different modes. So there will be no variation in fields as the value of P keeps on changing. So I can have absolutely uniformity in radiation characteristics. But things are not that simple, as you will realize. In the practical design, other things come which will complicate matters. You will see. We have already covered this. We are not going to go here. This is the final form of the Green's functions. Actually, this is GH-MY-HY because the slot is Y directed. This is the radiated HY component, which is the final form of the Green's functions. So, but anyway, we have, and you note the 2 summations over M and N. Okay. So we'll go to now the results. So this is our investigation of a 3-layer hemispherical DRA on a microstrip substrate. It has 3 layers. These are the photos of some of the representative photos of the shell, which we made of permittivities 9 and 4. And this is some of the results which we obtained. Now you see that this is for the centrally located slot. You see this is a centered slot. So you now go back to the first figure which we started our this session in. So this is a 3-layer configuration now. This is a slot, and all the dimensions are given by doing a so it is a centered slot, which is the slot located in the center of the DRA. The offset is 0. So we have the first mode excitation, which is the T111 mode, and the second mode is the stub resonance. We all know we all know that a microstrip stub is used in a microstrip line design, in a microstrip patch design. The microstrip stub, which is this length of line, it is kept open circuited. So this is used in order to match the slot with the patch. To enhance the impedance matching. It has no other purpose. But here it is to show that the same configuration, if I go, the same configuration can be used in order to enhance the bandwidth. So the stub produces another resonance which couples to the DRA resonance in order to enhance the bandwidth. This happens because the DRA modes have relatively lower Q factor. You know, we characterize the Q factor of a mode by this relationship. Each mode can have a different Q factor, QMNP. So we can choose appropriate modes which have a lower Q factor, and they will couple. A mode with a lower Q factor means what? A mode with a lower Q factor means it can couple. This is a mode with a high Q factor. Let me just clear this. I think it helps. Now let me. This is a mode with a high Q factor. Because its bandwidth is small. Or 10 dB bandwidth. It is small. This is a mode with a lower Q factor. It has a larger impedance bandwidth. So this mode has a high Q factor. This mode has a low Q factor. If there is any nearby resonance, this mode has a tendency to couple with any resonance because it has relatively a wide band. Okay, so you see lower order, low Q factor modes tend to give me broadband behavior and also helps me to couple with nearby modes to further enhance the bandwidth. So you see now, this exactly happens here. So the first mode is the TE111 mode. The second one is the stub resonance. The stub resonance provides another mode in order to couple with the TE111 mode and enhance the impedance bandwidth to 29%, which we can never do for conventional microstrip patch designs. Okay. So this kind of mode coupling extends the impedance bandwidth, further extends the impedance bandwidth of a DRA. So this is the next important step, which is showing the frequency tuning. If I choose, this is again with the centered slot, and by choosing different DRA dimensions, R2 as 18.5 here, if we look at here, 914 combination of permittivity, R1 12.5, R2 17.5, R3 22.5, and here we have R1, R2 18.5 and R3 23.5. We can we can do a frequency tuning of this configuration. In this frequency tuned configuration, which is resonant at another frequency band. So this is from 3 to 3.5, and this is from 4 to 5. The first resonance is the stub resonance, and the second is the T112. You see the value of P is changed. Value of N and M is the same. That means the radiation characteristics are going to be the same, because radiation character only depends on N and M. And it will change, the changed value of P, which is 2 here, will change only the resonant frequency. So the resonant frequency is changed, but the radiation characteristics remain absolutely the same as before. So you now see how the Green's function enables us to understand the radiation properties of the modes and to select appropriate modes for satisfying the vendor requirement, because everything will depend on the excited modes of the structure. So the first return loss dip is T11 stub resonance. The second one is T112 with an impedance bandwidth of 30.1. Now let us go to an offset slot. This slot is offset along the y-axis. It is a y-offset slot. Along the slot length, it is offset along the slot length with the x offset 0. We now see that it is an excitation of 2 pairs of modes here and 2 pairs of modes here, with the slot resonance at the center. So you see, as we predicted before, because the DRA modes are of a lower Q factor, they combine with the slot resonance from 2 sides and give me a very wide impedance bandwidth. However, it comes with a price. There is a degenerate T201, T221 excitation. Why we call degenerate? You see, the values of N and P, 2-1 are the same, which means that they have the same frequency, resonant frequency, because the resonant frequency is only dependent on N and M. But they have the value, which is the value of M is different, which means that their radiation characteristics are going to be different. This is bad news for us. And we need to now take care of the polarization purity aspects at this resonant mode. Because if that is not taken into account, these two modes can have destructive interference on their radiation characteristics. So you now see how the Green's function again helps us to isolate the problem and to take appropriate steps to minimize the problem. How it can be minimized? Because the field configurations depend on N and M, we can appropriately locate the slot. We can appropriately locate the Y offset so as to selectively couple with any one of the two modes. These two modes can potentially be excited, but we will try to adjust the slot offset such that one mode gets preferentially excited over the other. Though you cannot stop the other mode from getting excited, but there can be a lesser chance of polarization impurity to happen. So now we have the T2T1, 201, excited at 4.56. The second resonance is at 5.28, which is the slot resonance, and the third resonance is the T202 and the 222 resonances. Note here that the value of P is changed, 2 here, 1 here. So the resonance frequency is changed. However, the radiation characteristics here and there are the same because the value of N and M are the same. So the problems here also gets manifested there due to the coupling of these two resonances. The measured 10 dB impedance bandwidth is 43.42. Now, the slot offset along the slot width. If you were to offset the slot along the width of the slot with no offset along the length, we would actually excite one kind of mode, which is TM here and T there. You see, it is a coupling. The bandwidth is given as a coupling between the TM mode here and the T mode there. This coupling is going to be not beneficial for us because TM modes typically have an end-fire pattern. TM modes typically have a pattern like this. And T modes have typically a pattern like this. When I say typical, it is typical, but not universal. There are T modes. There are T modes which have an end-fire pattern. So you have to be very, very careful. For example, the T221 has an end-fire pattern. Okay, so you need to be very careful of the modes. So, but in general, T modes have this kind of pattern which are used in satellite communication, and these kinds of the TM modes have an end-fire pattern which is typically used for surface or vehicular communication because it is radiation along the horizon and it is radiation skywards. Okay, so now if your this one is exciting the TM and the T mode simultaneously, that means across the impedance band, your pattern characteristics is going to change from end-fire here to broadside there. So this kind of slot offset should better be avoided if you are concerned with the pattern stability. If you are not concerned with pattern stability, like in-road applications, where the pattern shape does not matter, you radiate any and how it is going to be okay in a limited space, it is fine. But depends on the application. But you need to be careful that such a slot offset has a potential excitation or enables a potential excitation of the TM mode on one side and a T mode on the other side, leading to pattern degradation across the impedance band. So the pattern characteristics here is 21.1.52 impedance bandwidth, which is slightly lower than the this one, the Y offset case, and sorry, slightly lower than the centered slot case and quite lower than the Y offset case. So these are the typical radiation patterns of the 3-layer hemispherical DRA fed by the centered slot. These are the radiation characteristics of the Y offset slot. You see that the pattern in the YZ plane is asymmetric because the slot is offset along the Y-axis. The pattern along the XZ plane is symmetric because the slot, which is a Y offset slot, it is still symmetric about the XZ plane. Just think of it. If the slot is offset along the Y-axis, the slot is still symmetric about the XZ plane, which makes the XZ pattern characteristics uniform or stable. Yes, symmetric. While the YZ pattern characteristics is asymmetric. So these are some of the bandwidth investigations for the structure for the microstrip 3-coupled layer as a function of this one, epsilon R1 and epsilon R2. So we find that here epsilon R2 at about 1 and epsilon R3 around 4, we get typically the maximum bandwidth characteristics. Okay, so 1 or 4 or 3, we get the maximum bandwidth characteristics. And also we plot the quality factor of the T111 mode. We see at the same frequency, at the same value of epsilon R3, we get the minimum of the quality factor. Okay, so these are the quality factor and the bandwidth characteristics of the T111 mode. Now we have another configuration, which is the probe coupled. So for the probe coupled, the same thing can be done, but we are not going to go to the analysis. It is another big formulation. But if we do the analysis of this structure, we will find out the bandwidth characteristics was found out. You can look at our work. A number of works were published, some of them in IEEE transactions and some of them in IEEE antennas propagation letters and some in IET. So I did not list the works, but you can do a Google search and find out the works which are relevant to this work, to this presentation. So so we have the TM101 mode, which are here, and the probe resonance, which is here, and they couple together to give me a wideband characteristic. Okay, so the coupling between the TM101 in fire mode and the probe resonance gives me the wideband characteristics, and with a radiation pattern which is like this. Okay, so you see the in-fire characteristics, and if you go to the bandwidth characteristics, it is giving me a bandwidth characteristics of this with a maximum bandwidth at epsilon R3 at 3 and epsilon R2 equal to maybe 1, 3. And I think the first layer we chose as 9. And these are the Q factor. You again see that at the point of maximum bandwidth, the Q factor is the lowest. So this is the kind of bandwidth we obtained with a theoretical estimate. With theoretical numbers, we this one. Epsilon R3 2.75, the bandwidth was 63.68. But when we truncated that to round whole numbers with epsilon R1 9, epsilon R2 4, and epsilon R3 3. So 4, 3. So we chose this point actually 4, 3, 4, 3. So this dotted curve. So choosing this curve enables us to get a bandwidth of 63.22%, and most importantly, the radiation characteristics stay absolutely uniform, which is unthought of in the microstrip patch. This kind of bandwidth is unthought of in the microstrip patch, and in addition, the radiation characteristics of the DRA stay absolutely uniform across this bandwidth. So the radiation bandwidth is the same as the impedance bandwidth. So next, the last configuration we had was the rectangular waveguide coupled multilayer DRA. Full-fledged analysis of this appears in an IET paper, which was previously called the IEEE Proceedings on Antennas and Propagation from the UK. So this is a rectangular waveguide slot coupled to the DRA. Now again, this is itself a very big, there are several parameters to the design, and it is significantly different from the microstrip microstrip line slot coupled to the in-layer DRA. In a very short way, the rectangular waveguide is a difficult structure to match. It essentially provides the advantages of a high power, because the rectangular waveguide can carry high power, and also it is a kind of feed which is isolated. So it does not interfere with another kind of feed which can be placed in the vicinity. So reduced interference and high power are some of the key advantages of the rectangular waveguide feed. But to match a DRA with a rectangular waveguide is relatively much more difficult, because the rectangular waveguide is a non-TEM structure. While the microstrip line is a TEM structure, the coaxial probe is a TEM structure, quasi-TEM or whatever. But the rectangular waveguide is strictly a TE or a TM structure, which makes it difficult to match a DRA. A single layer DRA is very difficult to match. There has been many attempts or a lot of research in this area. Many different designs were proposed. And one of our contributions in this area is to use the multi-layer configuration in order to match the DRA to the waveguide. We are just going to give you the multi-layer works as an impedance transformer, which is transforming the like the impedance of free space to the slot impedance. So in the case of this kind of formulation, we have to take into account the ground plane thickness as well, because the results are very sensitive to the ground plane thickness. So that is taken as a rectangular cavity. So the method of movement gets more, in that sense, more general. I don't use the word difficult. It gets more general, that the slot has to be taken as a cavity. How? It is just like this. If I have a slot like this, and the conductor thickness is considered, this is a thick conductor. This is the thickness of the conductor. So I will close it by a magnetic current M1. I will close it by a magnetic current minus M1. I will have another surface here. I will close it with a magnetic current M2 and minus M2. So this is this region is a closed cavity. Okay. So that is how a ground plane thickness is considered. So it makes the method of movement with more variables, and we have to consider the Green's function of the closed cavity. So finding results in the rectangular waveguide is actually a bit more difficult than the slot coupled case. But anyway, don't worry about the product of double integration technique. We cannot discuss that. So this is the result which we obtained, which is the coupling. In fact, coupling to the rectangular waveguide is one issue, how the DRA couples to the waveguide, and next is the bandwidth issue. Okay, so we optimized the design and we got an impedance bandwidth of about 12.9%. And in addition to using the multi-layer geometry both as a coupling to enhance the coupling and to enhance the bandwidth, okay, simultaneously. So anyway, probably this is the last slide, and where are the radiation characteristics of the rectangular waveguide fed DRA. This is the results for the rectangular waveguide with the slot offset along the y-axis. You see the dominance of the slot resonance here. Okay, and here it was the coupling of the T112 mode of the DRA and the slot resonance to enhance the bandwidth. So here the relative dominance of the slot resonance. So it is the first weak resonance is the T112, and the second is the slot resonance, but the impedance bandwidth is a lot less. Instead of 12.9%, it is 5.42. So a centered slot is preferred for the rectangular waveguide. So probably this is the end. The only thing I would like to say in conclusion is that in addition to this, any kind of antenna structure where we are, let's say this antenna, if you are finding out the radiation characteristics at this resonance frequency, this will have contributions, though the principal mode you see is T111. The principal mode is T111. It will have contributions from all other modes. The Green's functions, though we have not dwelt on this topic because we didn't have time, the Green's function can help us to evaluate the relative modal contributions. The Green's function can help us to evaluate the relative modal contributions for all the modes at this resonant frequency, and help us to quantify how much the strength of excitation of the desired mode is relative to all the other modes. Okay, so you can see it that by looking at this kind of a Green's function, where we wrote down the we didn't write here the explicit form of the how the radiation fields are obtained, but you look at this equation. So you see, this is the Green's function due to the slot in the upper part, GMyHy. This is the radiated field. After I have found out the Green's function, it will be in double summation format. I can concentrate on finding the near field and the far field characteristics of any particular mode by stopping the double summation. If I stop the double summation and restrict myself to a particular mode, I can find out the radiated magnetic field due to a particular mode after knowing the magnetic current. So after solving the problem or knowing the magnetic current, I can find the radiated magnetic field, the near field, far field, intermediate field, whatever, by appropriately writing or appropriately selecting the modes here. That means I can find out the radiated power due to individual modes using this formulation. That means in this scenario, I can quantify the power radiated by all the modes at 3.08 gigahertz in addition to the T111 mode. If I find some other mode is actually causing a lot of radiation here or stealing power from the T111 mode, we can zero in on that mode. We can take care of that mode and try to take steps so as to minimize its interference. So therefore, the Green's function also helps us in a systematic and a scientific diagnosis of the problem as to which modes are causing a deterioration in the radiation characteristics. Okay, but anyway, if you are again interested, this also appeared in one of our IIT papers, so you can have a look at that. The mode excitation characteristics and how the modes are identified from the relevant modes, the power in all the modes are quantified and relevant conclusions can be made due from an excitation perspective of different modes. Okay. Anyway, so we conclude our presentation here, and I'm open to any questions which you may have.
Participants are requested to ask if you have any queries, please.
Hello.
Yes.
Sir, there are 4 questions that are placed on the chat box.
Shall I read
I think Roshendra Babu has placed these questions.
Shall I read out the question?
Wait. Now,
Roshendra Babu, can you ask your questions directly?
Yes, sir. Yes, sir.
if you can ask your questions, that will be better. Because
Yes,
I'm
sir.
new
Yes,
to
yes,
we usually use MS Teams in our classes and in other lectures. So I'm new to this Zoom. So
Yes, sir. I will ask the question.
presentations in Zoom elsewhere, but still I don't use it often. So yeah, you can ask your questions. Yeah, go ahead.
So as you have mentioned as one point, so we use this DRA in low loss radiating applications.
Yes.
Sir, may I know what are the real-time applications where we have this low loss radiation?
Any kind of, like applications where we need a good, efficient and a miniaturized radiator. One of the things which goes I was saying in favor of the DRA very much is it's not only its low loss, but most importantly, its independence of radiation characteristics for a wideband application. the amount of bandwidth we can get, and the uniformity of radiation characteristics across the bandwidth. That very essentially distinguishes the DRA from the traditional configurations like the microstrip patch. Again, microstrip patch is not bad. It has stood the test of time and it has enormous application. And one of the good things which go in the favor of the microstrip patch is its conformal nature. It can sit on any kind of surface. Okay. Typically, the microstrip patch is difficult to miniaturize. We won't go to the details of that. Like if you look at the antenna literature and even look at attempts to miniaturize or convert the microstrip patch to an electrically small limit, you would find that actually they say that the microstrip patch is essentially a capacitor. It is a capacitance formed between the upper metal plate and the ground. A capacitor is inherently not a good radiator. Though we know that the microstrip patch reduced by the fringing fields, but that is fine. But we see that the microstrip patch has relatively much poorer bandwidth and radiation characteristics, stability of radiation characteristics across the impedance bandwidth. Okay, and in addition, to the low loss characteristics essentially contributed by the lack of any conductor on the DRA. So in any kind of application where we need an efficient radiator, the DRA will find efficient wideband radiator with stable radiation characteristics. It will find its application, very polar application, satellite communication applications, naval applications. It should not be any problem.
The next one is in the present slide, that 43rd slide. Sir, what is in the previous slide? Sir.
In the previous.
Okay. Yes, 43.
Yes.
Sir, here in that result A, so what kind of effect shall we have during the transmission or reception, sir? As we have the middle one is the resonant frequency, isn't it, sir?
No, there are essentially 3 resonances here.
Yes, sir.
3 resonances, and they are coupled together. So what we want, either in the transmitting or because the receiving problem is the reciprocal of the transmitting problem. What will happen during transmission, the opposite thing or the reciprocal thing is going to happen during the reception. So if we want a good radiator, if we want a good receiver, we also want the antenna to be a good radiator. So therefore, we must look either in transmission or reception at the stability of the radiation pattern across this impedance bandwidth. You see, we are claiming a 43.42% impedance bandwidth. Yes. But if the radiation patterns are not stable across this impedance bandwidth, most of the vendors who want broadband antennas also say that I want radiation characteristics which are stable across the band, not only an impedance band. Okay. So here we need to take care that the radiation pattern here, the radiation pattern of the first resonance, second resonance, and the third resonance are to the maximum extent similar. Yes. We want to avoid the excitation of degenerate modes like T201 and T221. But we realize that such degenerate modes can and will get excited. But we have to be aware beforehand that there is a danger lying here. The Green's function points to a potential danger lying there or a potential problem lying there. So we have to take care that the T201 or the T221 gets preferentially excited depending on what kind of radiation pattern I want. Okay, so these are the issues surrounding this kind of design either during the transmission or during reception. Okay.
Sir, one more question, sir. How can one try exciting the degenerate modes systematically without trial and error?
Can you repeat that question a little bit louder, please?
Yes, sir. How can one try exciting the degenerate modes systematically without trial and error?
Actually, the answer to this question is one cannot. Trial and error has to happen, but we the Green's function at least gives you a lot of transparency. Okay, it gives you a transparency in the sense that it tells you that these two are degenerate, and these are the field configurations of the degenerate modes. We can plot the field configurations of the T201 and T221, and we can find their relative field orientations. Now we can do a trial and error. We have to do a trial and error by selectively moving the excitation or the slot source by coupling with the appropriate mode. That is inevitable because you have to match the slot with the antenna. So some trial and error will be there, but you do the trial and error not as a blind man walking with a stick. He does not know where to go anywhere. You know where to concentrate. You know where the problem lies, at which frequency the problem lies. The Green's function points its fingers to the particular frequency and the particular problem, so that now you can zero in on that problem and do some trial and error to remove that problem. Essentially, you have to look at the field configurations of the T201 and T221. If you want to preferentially excite T201, your slot should be located in such a way such that its electric and magnetic field configuration matches with the T201 mode. Typically, you are looking at the magnetic field because the electric field on the ground plane is 0. You are looking at the magnetic field, the tangential magnetic field on the ground plane for the DRA modes. Those tangential magnetic field has to excite or has to orient with the magnetic field of the slot in order to excite that mode appropriately. Look at this. A slot on a ground plane. If you want to have this slot, if you want to excite the proper mode in the slot, you have to look at the tangential magnetic field. If this is the tangential magnetic field which is excited by the relevant mode, its relevant current is in this direction, because N cross H is equal to J. What you want the slot to do is to orient the slot perpendicular to this current. This is 90 degree, so that this current continues as the displacement current in the slot. So you orient the slot in the region where J is maximum, and the slot should be normal to this J, such that this appropriate displacement current gets generated. Or you can say that if this is the slot magnetic field, H slot, the magnetic field due to the appropriate mode of the DRA on the ground plane, the magnetic field due to whatever modes we discussed there, on the ground plane should match with the magnetic field of the slot. This is how we preferentially excite one mode over the other. Okay. Now all this is on the blackboard. These are guidelines in any kind of design. Okay. Now you have to, armed with this background as to what is happening, now you have to do a bit of trial and error, which are rather minimized to excite the particular mode.
So, shall I go for the next question, sir?
Yes, sure.
Sir, which feeding technique is more efficient to feed DRA, slot couple or direct microstrip line?
Okay. So if you look at the, again, this one, if you have a slot on a ground plane, you are comparing this configuration with this kind of configuration. The microstrip line directly lies over the DRA. So this is the microstrip line. Okay, the DRA rests on this, and this is your ground plane. So this is the microstrip line feed to the DRA. So this is the MSC. Now you see that in this case, the radiation from this microstrip line is rather shielded due to this ground plane. So we call that the feed radiation, the stub radiation and the radiation due to the feed line is shielded from the ground plane due to the presence of the ground plane. Here, there is a lot of chance of spurious radiation from the microstrip line. So this is one of the most important characteristics when you want to investigate the type of feed. This will also happen in the coplanar waveguide feed to the DRA. Okay, because there the DRA is going to sit on a ground plane and the coplanar feed is going to come in this fashion. Let us say this is a slot feed using a coplanar waveguide line. So this is all the ground plane and this is the coplanar feed, and the DRA sits on top of this. Oops. Whatever. Imagine this is a DRA. It is sitting on top of that. So now you see the radiation from this feed, these feed lines, this area. They will directly contribute to radiation from the DRA because it is a uniplanar design. Okay, it is a uniplanar design. So the DRA radiation characteristics will be somewhat, may potentially be degraded, due to the spurious radiation from the feed line. Whereas in this kind of feed, the feed radiation is shielded due to the presence of this ground plane.
Sir,
Any others?
sir, last question, sir.
Yes.
Do we have any limitation with respect to the size or the frequency we can work with the DRA?
Louder, please. Could not hear you.
Have any limitation on the size and the frequency to work with the DRA?
We always control we essentially control the size and more often control also the permittivity. The more the permittivity of the DRA, the lower the resonant frequency. The lower the permittivity of the DRA, the higher the resonant frequency. The lower the size of the DRA, the higher the resonant frequency. The higher the size of the DRA, the lower the resonant frequency.
Okay.
So we will choose accordingly. Note that we typically do not like to go, typically do not like to go over 20. Okay, we typically don't want to go over 20 in DRA because of the loss characteristics of high permittivity substrates.
Okay, sir. Thank you, sir. Thank you so much, sir. So, participants, if you still have any questions, please feel free to ask the questions. Sir,
Hello.
there is one more question by Amira, sir.
Sure, please go ahead.
Can the thickness of the DRA be less than the guided wavelength of the DRA?
Can the
Thickness of the DRA.
wait.
Yes.
Can the thickness of the DRA?
Yes, sir. Be less than the guided wavelength of the DRA.
Because the guided wavelength will be given by lambda naught. Okay, you are saying the guided wavelength inside the DRA. Guided wavelength inside the DRA. In the relevant permittivity region. Is that what is the question is?
Yes, sir.
Because we are not establishing, let's say if I'm considering the different layers of the DRA, even if you are considering the different layers in the DRA, so this particular distance has a very important role to play in impedance matching, and essentially I would say interaction with the feed, whether the feed is offset, how much is the layer thickness, how much is the layer permittivity. All these things are interrelated. So these particularly affect the impedance matching. So this layer thickness can be lower than the guided wavelength. Okay, we don't have to have a guided wavelength thickness inside the DRA. We don't have to have a resonance, so as to say a resonance within a layer. We are not considered about the resonance within a layer. We are considered about the resonance inside the whole structure.
Okay. Thank you, sir. Thank you so much, sir. Sir Ramakrishnan, sir.
Hello. Hello.
Hi. Yes.
We are done with the questions, sir.
Thank you very much, Brighton sir.
Yeah, sure. I can hear you.
Thank you very much for sharing your research experience to us. The participants are enlightened with many mathematical analysis and research areas with your lecture. We are very much thankful to you. Thank you very much, sir, for accepting our invitation and participating in this program.
Thank you very much. It is my pleasure to interact with you, and it is always good, so that, as I told you, that some of you take up this challenging work, in which the antenna analysis is done. Antenna simulation is good, it is not bad, but there are very important applications of antenna simulation and antenna analysis both. So also take up antenna analysis role. So that I would request at least some of you.
Okay. Thank you very much, sir.
Thanks.
Sir. Okay, dear participants, the afternoon session will be started by 2 o'clock, and I request you all to join by 1:45 p.m. In the afternoon session, Professor Mrinal Kantimandal will be the speaker, and a small change is today's afternoon topic is electronic switches in millimeter wave technology. Actually, in the schedule, it is given as the topic for the 21st, that is tomorrow's first session, but it is changed. Today's afternoon topic is electronic switches for millimeter wave technologies. Professor Mrinal Kantimandal of IIT Kharagpur will be handling the session. So I request you all to join by 1:45 p.m. sharp. Thank you very much. Rajshekhar sir, you can stop.